Hello, everybody. Good afternoon or good evening to some of you, I guess. I'm Krishna Garikipati, and it's my pleasure to welcome you to this first of our parallel semi-plenaries at the 16th USNCCM. It's also my pleasure to introduce my friend Jim Stewart, and more importantly, a very leading light in computational mechanics. Jim obtained his PhD from Stanford around 1996, moved almost directly to Sandia National Labs, where he has been ever since. From his early work, Jim has expanded out to essentially being an expert on many aspects of computational mechanics. His original training was sort of related to error estimation, and from that he's gone on to things like verification and validation, and is a very important figure now in uncertainty quantification also. Jim has played many roles at the labs, and I just mentioned where he is right now. He's now a senior manager in the computational science and mathematics group, which includes, computational mathematics, computational multiphysics, computational multiscale, as well as computational science. Over the years, he's also played a very important role in many of the major computational thrusts at the lab as we went through the pettascale and now into the exascale era. Jim has interacted with universities and researchers across the board while driving research and, of course, conducting his own top-class research. It's a great pleasure to welcome Jim to this semi-plenary and get this started. Just one thing about how we're going to run this. We'll let Jim get on with the talk, and if you have questions, you are encouraged to put them in a box that you should see on your screen saying something to the effect of "Ask Jim Stewart a question," and that will get relayed to us here, and I will present Jim questions at the end of his talk. With that, I'll just remind you all you're all muted, so we will get started. Jim, all yours.
All right, thank you, Krishna, very much for the introduction. I want to thank all the organizers as well. This talk is veering in a direction perhaps new and a little different from most of the topics here at the conference. So I'm looking forward to communicating with you some of the challenges here with Exascale. I have a lot of colleagues that I want to thank at Sandia who contributed both content and guidance to the presentation. There are a lot of names here, and there are many more in the background, but I want to make sure these folks all get acknowledged. So I want to start by asking the question, what is exascale? And the definition is a billion. So we're talking about 10 to the 18th floating point operations per second. It's important to note also that this capability does not exist today, but soon will. And pictured down here in the lower right is the Summit supercomputer at Oak Ridge. Before going into some of these challenges, I want to lay out some of the landscape of these supercomputers. And this slide shows, I pulled it from the top500.org. Now, this is a list published every 6 months that lists the top computers in the world, and it was last published in June. So this is literally hot off the press. This list here is the ranking according to the high performance LINPACK benchmark, which is the most common benchmark. I'll speak to a few other benchmarks momentarily. So a lot of information here. I wanted to start by highlighting the different countries that these computers are in. In blue here are the 6 machines in the top 10 here that are in the USA. You also see the top computer, Fugaku, is in Japan. China has 2, Europe has 2 in this list of top 10. I want to point out some other information. In the red colored, the red numbers here are the speed ratings, and you see what those are in petaflops. So the top machine, Fugaku, is 442 petaflops. That's almost 3 times the speed of Summit, which is number 2. And then you see Sierra number 3, and the numbers go down from there. Also so I'm going to also point out 442 petaflops is not quite halfway to exascale. So we still have ways to go, although we're making good progress. In the column to the left of the red are the power requirements from these machines. So you see Fugaku is almost 30 megawatts of power. And then finally, in the rightmost column, you see that some of these machines have GPU accelerators. So these are the graphical processing units. 6 of the 10 on this list are GPU accelerated, all with NVIDIA GPUs. So what's behind the numbers? I had to go back to the November list to get some of these trends, but let's take a look. In terms of aggregate performance, there's been a leveling off in the top 500 list. In terms of processors, there are certain companies that dominate. In the CPUs, Intel has 90% of the systems. For the GPUs, there are 149 machines in the top 500 that have GPUs. 140 of these use NVIDIA chips. And then also AMD is on the rise. Only in terms of both the CPUs and the GPUs, we're seeing more AMD on the scene. The country leads, it depends on how you count, going just in the most recent list. China leads in terms of number of systems with 188 systems. US is second with 122. In terms of total aggregate performance, the US leads. Japan is second, China is third. Most of Japan's, of course, is because of Fugaku. So now I talked about the HPL benchmark. There are other benchmarks as well. The high performance conjugate gradient benchmark is more reflective of some of our computational mechanics workflows and data structures. You see a lot of the same machines on the list, but different numbers. The petaflop ratings are quite a bit slower on this benchmark. Over here on the right is the top 5 computers for another benchmark that is really focused on the AI workload. So these are the mixed and lower precision workloads. And you see the top 2 machines, Fugaku and Summit, again, have reached exascale. So you could argue that we're already there, but certainly for our computational mechanics problems, we have a long way to go. And then the green 500, again, this is about computational and power efficiency. You see the list here, the machines are sprinkled across the top 500 list. A couple of the top 10 machines from the HPL benchmark are also in this list. So now let's look ahead. One of the machines on the list that I just showed was Perlmutter. Now Perlmutter, it's at Lawrence Berkeley National Lab. It's the world's newest supercomputer. It's literally being made available and put into service this month. It's interesting in the sense that it's in the top 10 of all 4 benchmarks I've discussed. So that's a very impressive result. However, at only 64.6 petaflops, there's a big gap here between where we are now in exascale. So let's look ahead and see what is coming. In the US, there are 3 machines that will be here in the next, say, 12 months to 24 months-ish. First is Aurora. This is going to be at Argonne National Lab. Aurora is going to be rated at 1 exaflop. It will have both Intel GPUs and CPUs. Then around the same time, the Frontier machine will appear at Oak Ridge National Lab in Tennessee. It will have AMD CPUs and GPUs. The expected rating is 1.5 exaflops. And then about 12 months after Aurora and Frontier, we'll get El Capitan. El Capitan is going to be at Lawrence Livermore National Lab in California. Its architecture by construction is about the same as the Frontier machine at Oak Ridge. It's projected to be 2 exaflops. So obviously with this landscape, the US systems, we are all in on GPUs. Not only that, we're diversifying a little bit away from NVIDIA towards these other vendors. And so I wanted to, from that background, lay out the rest of my talk. It's going to be focused on GPUs, this hardware heterogeneity and how to get scalability on these machines. I've sprinkled 3 applications in here in the blue. And then these other topics are very important additional considerations in our transition towards the exascale. So I will highlight, and this will be a very high-level journey through these topics in the short time that we have. So let me start with portability. So portability is meant to address the challenge here with the cognitive loads on the developers. Now, these systems, even the GPU systems, are different enough. They have different sources of concurrency, different memory layouts. The way you have to manage memory is much different. And so the idea here is to provide an abstraction layer to ease this load on the developers. Our solution at Sandia is a layer called Cocos. It's an open source abstraction layer. There are others as well listed here in the lower left of the slide. The Raja system at Lawrence Livermore is very similar to Cocos. There's Legion coming out of Stanford. It's similar in goals, but it's focused more on task-based programming models. And there are others as well. But the idea here is that with these layers, we want to make developers productive on these systems on day one. I will add that the Cocos team, and I'm sure these other teams as well, are already working on these new advanced systems. They get access to the early hardware. They're already building the backends needed to get performance on these new systems when they do come online. So that's all I'll say about portability. And I want to move on to my first application, which is a hypersonics application. At Sandia, we have a code called Spark. It's our virtual flight testing platform. It's got a lot of advanced capabilities like non-equilibrium chemistry, various turbulence models that make this an exascale kind of application for us. The picture here shown, you can see this generic cone-shaped vehicle, which is a generic vehicle, the thin boundary layers along the surface. The top picture is a RANS turbulence simulation. The bottom, you can see much more detail in the flow field with this wall-resolved LES model. Spark is coupled to a lot of other codes. It's built on Cocos, making it mostly platform agnostic, which is the primary goal here. Now, I want to shift towards the capabilities to the performance and talk mostly about how these codes are doing on these advanced platforms and then highlight some of the challenges here. Shown here is a strong scaling plot. There are two sets of curves here. The set on the left is with a coarse grid of 4.2 million elements. The set of curves here on the right are the fine grid with almost 270 million elements. Now here, lower is better. This is elapsed time. You want linear scaling would be perfect scaling, and you see these tail offs here. So there are several machines represented here. I want to focus on two, Trinity and Sierra. So Trinity, as you see up here in the upper right, is the number 16 machine in the HPL benchmark. Sierra, I already mentioned, is number 3. Sierra on this plot is the only GPU-based machine. Trinity is not. Trinity is based on the Knights Landing CPU mini-core system. And so right away, you see that the GPU Sierra system is much lower. It's 2 to 8 times faster, depending on where you measure, than the CPU-based systems. You also see the tail off, and I'll come back and talk about what is contributing to this tail and the strong scaling limits. On the GPU, the Summit machine, now these scalings go to about half of the Summit machine and about 1/3 of Trinity. So that's what we're looking at here in terms of the amount of the percentage of the machine that these plots are taken on. I want to mention with the GPU machines, this is a throughput plot, and it shows the efficiency of work done on these processing units. So the bottom set of curves, which are the generally flat curves down here, show that the efficiency or the throughput of work is basically independent of the amount of work on the CPUs. You can see by the red line, though, that the GPU system is not that way. In fact, the more work you put on these GPUs, the more efficient it becomes. And you can clearly see that these GPUs thrive with more work. The 2 to the 28th here is the 270 million element case that I showed on the previous chart. And so again, the higher the GPU workload, the higher the rate of work performed. So now let's go back to the scaling plot I just showed and point out, I want to talk about these tails here. So the first major contributor to these tail at the strong scaling limit is I/O. Now these I/O challenges exist independent of whether you're GPU or not. If you happen to watch Bob Taylor's presentation an hour ago, he mentioned I/O back in the 70s when they used computer punch cards and then printer paper as your output. So fortunately, we're not that slow. We've moved on greatly from there, but I can tell you on these machines, I/O is a big challenge, and it's a work in progress to get it to where it's not dominating at these strong scaling limits. So this is a challenge on all platforms, but on GPU platforms in particular, there are additional challenges. And you can see this strong scaling limit issue appears on both the coarse mesh and the fine mesh strong scaling studies. And it's really about the memory and the data. And I want to go through these issues because they're all important. First of all, I mentioned that the GPUs thrive with more work. So when you reduce the amount of work on a GPU, they slow down and other things start to dominate. And these GPUs are so fast that if they don't have work to do, then you see this tail off. Also, there is an irreducible launch latency associated with getting work over to the GPU. So when you have to move and fire off a function and transfer data over to the GPU to execute that function, there's a latency that you can't reduce, and that's seen here as well. And then finally, there's an overhead of MPI. Getting data, just strictly getting data on and off the GPU is expensive. And let me use this opportunity then to go to my next topic and talk more about MPI. And briefly, I will mention some of the challenges here. Last month, the MPI Standards Committee released a new version of MPI 4.0. This is significant because it's the first release of MPI since June in 2015. There are a lot of new features here. I've called out one called Partition Point-to-Point Communication, and this is a chapter of the standard that was authored by my colleague Ryan Grant. Now, what you see here in the bar chart is Mpi overhead. So this is a single rank, and what you see is as the number of threads goes up on that rank, the overhead of message passing goes up. And if you then compute the red and compare the red and the blue bars, the red is a more dense stencil, so there's more work going on. So the more work you have, the more threads you have, the higher the overhead. And that's what we're trying to solve here with this new version of MPI. So the way it works is through partition communication, which basically you bundle up these threads together so you're not individually trying to match send and receive threads. And so this is some work going on the side that I wanted to make you aware of because it does couple into allowing us to get our codes to perform on these new machines. And now I have one slide on co-design. So the interaction with MPI and the MPI standards group with our computational mechanics efforts really appears as higher up in this co-design hierarchy. However, moving forward, we're going to see situations where it's not just speed of these machines that dominates the design considerations. There are also swap constraints, and swap, as you see here in this box in the lower left, space, power, and weight. And the only way you're really going to achieve the space, power, and weight constraints, and we already talked about power when we looked at the top 500 list, the relatively big power budgets of these machines, you're really only going to accomplish this by going further down the co-design hierarchy. The next generation microelectronics, the new electronic and optical materials, there's a lot of research going on in those areas. DOE has significant investments in this entire flow throughout this co-design hierarchy. So I just wanted to mention that it's not just about speed, it's not just about the software, it's also about the microelectronics and the materials that are becoming more important as these new machines get designed. So let me go to my second application, Earth System Modeling. There's a video down here I'm going to let play a little bit, and then I'm going to pause it. So DOE has a huge effort in Earth System Modeling. It's called E3SM, Energy Exascale Earth System Modeling, and I'll pause it here for a second. The E3SM code suite itself has different modules. You see over here on the left, atmosphere, ocean, sea ice, land ice, and river. It's a big effort, 8 DOE labs, many universities. It's looking out decades in the climate. And the goal here is to make sure that these codes run efficiently on these upcoming exascale systems. So let me go back to the video here. This video is made through a compilation of simulations done with the first version of E3SM released in 2018. It is a storm resolving resolution of 25 kilometers of horizontal resolution. You can see the vortices form, the clouds and storms form. It's pretty, I think it looks realistic. It took a long time to generate these runs. Again, these weren't done on GPU systems. They weren't available at the time. But you can see what we're capable of doing with these exascale systems. We are moving towards being able to do these full global Earth system models and problems like this. So now let me move on and talk about the progress being made since 2018. And over here on the left, you can see that we've gone from a 25 kilometer resolution down to 3 kilometers and even 1 kilometer, which are now able to resolve clouds. You can see the visualization of a simulated storm cloud down here in the lower left. Now the scaling plot here is a comparison of let's not talk about the blue curve at the bottom just yet, but the rest of the curves are 3 kilometer resolution. And here higher is better. These are strong scaling curves again. The y-axis is simulated years per day. Now what the cluster of curves labeled CPUs is various implementations of the model on different CPU-based systems. And I'm not going to try to differentiate what those are. The point I want to make here is that the GPU implementation is an order of magnitude faster. And here, these scaling plots on the GPU, the red curve up there, was done on the entire Summit machine. And the reason you don't see the strong scaling tail off is because of the model, the cloud resolving model, which I'll talk about here in a second, keeps the GPUs loaded with enough work that we don't see the strong scaling tail off. So let me talk about the model. The model itself is a tracer transport model. Now, a tracer is just a representation of a trace constituent. It could be water, vapor, it could be ice, or various aerosols. So the more tracers you have, the more physics you have. If you look at the scaling plot here, now this is, again, simulated years per day, so higher is better. But if you just compare the solid and dashed lines, you see that when you add tracers, which the dashed lines do, the model slows down because you're doing more work. But let me talk about the algorithm. Now, what we've done is we've moved from a pure Eulerian implementation to a semi-Lagrangian implementation of this tracer transport. The advantage here is that it allows for computational speed, and the speed is realized on all platforms, CPU and GPU. However, for GPUs, there's a particular advantage here because, again, the communication reductions enabled by the semi-Lagrangian implementation provide advantages on the GPUs that because of the overhead of communication. So you can see that if you compare the red and the black now, the addition of tracers to the semi-Lagrangian implementation is there's less of an overhead than it is for the Eulerian implementation. So it's very important to realize that when you choose an algorithm, there could be bigger advantages in the GPU case than in the non-GPU case because of the considerations around memory and data movement. And I'll have more to say about that as we move on. I want to go to another component of E3SM, which is the land ice component. This is a first order Stokes model. You see the pictures over here on the right. This is Greenland and Antarctica. Now the colors here denote surface velocity of the ice. And you can see the blue is slower. You would expect the ice to be moving more slowly in the middle of these land masses. And then the red color near the shoreline, the ice is flowing more quickly. And you can see the adaptive mesh refinement that we have to resolve that higher motion. Now to pull these calculations off, it requires a lot of inversion, parameter estimation that's massive calculations in and of themselves. So that's why these advanced analysis capabilities are so important. But I'm not going to talk about that now. What I want to talk about is the scaling performance. I'm just going to focus initially on this plot here on the left, which is a plot over time from 2018 till now, showing the improvement in the assembly time on GPUs. You can see the orange line, which is the GPU assembly time. Back in 2018, this was roughly twice as expensive as the CPU implementation, but over the 3 years, we've got it down to be 5 or 6 times faster than the CPU implementation. And this is done through smart memory management. It's just a realization that little things can add up. And I want to use as an example this first item, this memoization, which is just a simple concept. When you're gathering and scattering, say for residual computation, some terms don't change from operation to iteration. And in those cases, what you want to do is you want to store those terms and just use them again instead of moving data back onto the GPU every time and then redoing the calculation. So those are the kinds of things that we're doing to speed these codes up. This bar chart down here on the lower left shows comparison of 3 CPU systems against this P100, which is an early version of an NVIDIA GPU. And you can see just this simple operation gives a higher advantage in terms of performance on the GPU than it does on the CPU. I'll move on to the solver now and talk about our workhorse solver, Algebraic multigrid. Now, multigrid is an algorithm that offers very nice convergence properties through these cycles from fine to coarse grids, and you go up and down these cycles to achieve quick convergence. However, for exascale, there are new challenges associated with doing this, and this is really early. We're still really early in trying to work through some of these challenges. Now, when we're dealing with unstructured meshes, the irregular memory access presents a particular challenge for exascale, but there's also other challenges associated with the sequential nature by which you cycle through these grids. And let me now talk about some of the ideas we have for dealing with this. I mentioned the hierarchies. It's expensive to set these hierarchies up. So one thing you can do is reuse them. For example, if you're time stepping or you're going through an optimization process, you might be able to reuse these cycles. You can reduce the number of levels in your cycle, and that's what the picture shows here, that if you compare, say, a GPU and a CPU cycle, the GPU would, you might get more advantages by reducing the number of levels. And then the third thing on this list, I mentioned earlier about the launch latency of moving work onto the GPUs. So another idea is to fuse kernels, so you have to, you don't have to move this data over to the GPUs as much. And then I already talked about caching more data. We have one simple example here, going back to the atmosphere problem. This is just a simple test problem on AMG and its scalability. We've done a very small, strong scaling study here on the left on GPUs. Again, you see the tail here. This problem's too small to really get a thorough test of the method. The weak scaling out to 512 GPUs is looking better. I will say a comment though on these Earth system models. The unstructured grid is generally on the surface, and then we extrude vertically away from the surface. So the the mesh that's orthogonal to the surface is generally structured. And so you can take advantage of that when you set up these algebraic multigrid cycles and help take advantage of the structured memory layouts when you do that. So we're just looking into ideas like that. Now I'm going to change directions. I said this is going to be a high-level journey through these topics. I'm going to talk about workflows because the exascale workflow is a new challenge for us. I've got a schematic here of a very simplified workflow. This is oversimplified so I can make a point, but currently what you might do is in an analysis is you start with the geometry, you generate a mesh, you partition it, then you enter your code execution, you read the mesh, you enter your time loop, and then you post-process with your outputted data. Now, at exascale, that's not going to work. And the reason it's not going to work is because the input and output, which I mentioned earlier, becomes too large. You simply can't manipulate file sizes that are that big. And what I've suggested here is a new workflow that we're actually pursuing at Sandia in our applications. There are other ways you could perhaps do this as well, but I'll tell you what we're doing, and you can see the orange boxes, which are the new steps. Instead of generating the full mesh, we generate a coarse mesh and then read that in. And then we spread, in a parallel way, we refine the mesh inside the code in an in situ way. But to pull that off, you've also got to read the geometry in because you need to refine the mesh to the geometry. So you got to make your geometry a library now. I'll show some results here on the next slide. And then on the output side, again, there's too much data generally to dump the file all the time like we have in the past. So you want to find ways to do some data analysis while the code is still executing. I'll show an example of that as well. First, on the mesh side, you see the table here on the left. I've circled the 15 billion element mesh. So what we have done is we've done some case studies where we've read in a coarse mesh, done one level of refinement, and see how it performs. And that's what this plot here on the lower left shows. It's a small, strong scaling study where we've done two cases. This case here on the left is where we've read in R2, which is 236 million elements. That's our coarse mesh. We do one level of refinement to R3. And then in the second set of curves, we do the read of R3 being our coarse mesh, and then one level to R4. So the point here is you see how they strong scale. And the interesting thing here is that the refinement step, the in situ refinement, is actually much faster than the read step, which is encouraging. Soon we'll have another level of refinement. We plan to get to 120 billion element mesh very soon. And the challenge now is getting our codes to perform on those meshes. Now I'm going to move to the data analysis part. I'm going to walk through a simple example here. The example is compressible flow over a cavity. So remember, the idea here is all this stuff we could do today, but the difference here is we have to do it inside the code because we can't have access to all the data once the code stops running. And so what we see here, I'm going to walk through a particular piece of research that we have going today. And I'll start a little video here where you see the yellow spots down there. Now, these spots are anomalies, and these anomalies are being detected every time step. So you see an evolution of the yellow regions. And the way this works in this case, this is based on a machine learning approach where there are several steps involved. So basically, I'll show the steps here. You take the mesh, you partition it into elements, groups of elements, then you reduce the data on that mesh. And that's kind of a heuristic, and the simplest thing to do is to take your state values and just average them and compute a mean on each of the partitions in the group. Then you send that information to a machine learning clustering algorithm. In this case, we just use the commonly available dbScan algorithm. And then we detect outliers. And by that, we mean the partitions that have a value of your state variable, your reduced state variable, that has a value that's not close to its neighbors, that's an outlier, so we flag it. And note there's no physics involved here. It's just a machine learning approach. But what you can see is how these areas or these anomalies move over time as this flow goes across this cavity. The hope here is that this would inform an analyst to go take a closer look at what's going on and maybe try to understand the physics or maybe understand the source of the anomaly. So that's the idea. So this is very early work, but the benefit here, of course, is that you get data reduction, you get anomaly detection right inside the code loop. So now I'll move on to a different, my last application, machine learning application. And the setup here is with these new AI workloads, almost most of our applications now have some form of machine learned models as part of it for various things like reduced order models and the like. So you see machine learning becoming more integrated into our applications, in particular, these deep neural networks. And the question we're asking here is, can we scale the training of these deep neural networks? The problem setup is here where what we're trying to do is compute these parameters, okay, these parameters theta, and you can think of these as just weights on the nodes of these layers in this deep neural net. And what we have here is then an optimization problem. And the gradient descent optimization is what we use today. You can see the forward and back propagation. So the training data is input. You go through the layers to an output, you use that output to compute a loss function. And then in the back propagation, you compute derivatives with respect to the parameters. And then you can update the parameters and you go through that loop until you converge. Now, this looks painfully serial. There are ways to parallelize it. There are data parallel and model parallel ways where you basically slice up horizontally this network in various ways to try to get performance. What I'm going to introduce today or discuss today is a new research that we're doing in this area, and it's called layer parallel training. This layer parallel approach is modeled after a parallel in time stepping approach that we've recently published. The idea here is to slice these up vertically. So you assign various groupings of the layers themselves to the different processors. And the downside here, though, is that you get disconnections between these groups, and there's potential for errors to accumulate. And then, so what the idea then is to project down to this coarse grid correction step. Now, this is very analogous to our parallel algebraic multigrid approach that I just discussed, where you have a coarse grid correction. If you can control the errors between these groups of layers up here in the fine grid step, then the idea is that you can converge very quickly in the coarse grid step, and you can get parallel scalability this way. And so I've got one slide here on some performance. This is a test problem based using an MNIST, a modified NIST database of handwritten digits. This is a huge database that's commonly used for training these neural nets. You see a weak scaling and a strong scaling curve here, where the weak scaling, the purple is the layer parallel, the serial implementation is the green curve, and you can see a huge speed up here. In the weak scaling, we've kept the number of layers per core at 4. And in the strong scaling, similar good results. The 4 layers per core is seen at the strong scaling limit here. We've gone up to over 2,000 layers in this study. Now, this implementation here is available in this new package called Torchbraid. It's released as an extension to the commonly used PyTorch library. Now, I will add that the GPU work is in progress. This is really GPU agnostic. This just is an acknowledgement of the scale and the multi-programming parallel model that all these systems are having. But the GPU specific improvements are still to come. So again, this is brand new work.
Jim, just a quick heads up here. We're kind of coming close to about 7 minutes.
Okay, I'm going to wrap up on the next. Perfect. Thank you, Krishna. So let me summarize my key points. I've mentioned the hardware that's coming online in the US in the next couple of years. They're all going to be GPU accelerated, GPUs from different vendors. In general, though, there are new sources of concurrency. Now, MPI plus X could be threads or tasks. I discussed COCOS and mentioned the importance of the performance portability layer. The GPU performance, I hope you've seen through these examples, that it requires a rethinking of our algorithms. The GPUs thrive with more work. You want to minimize communication. Moving data on and off of these GPUs is expensive. And then the new exascale workflows, it's going to require embedded algorithms to even generate your mesh, to analyze the data before you go out to disk, and then the integrated machine learning as well. It's interesting, I wanted to go back in time and compare the June 2021 list with the list from 10 years ago. You can see the #1 computer 10 years ago was also out of the Riken Institute in Japan. It had a rating of 8.2 petaflops. And if you compare Riken, or the K computer with Fugaku, you see Fugaku is nearly 50 times or over 50 times as fast with only 2.5 times the power budget. So this is a very impressive gain, but we still have a long way to go. Another interesting fact is that in 2011, only the top 10 computers exceeded a petaflop. Today, all 500 do. And this is my final slide, what lies ahead? First, what lies ahead is exascale. We're not there yet, but we will be soon. Also, you've seen the US is all in on GPUs. However, you see with Fugaku and other machines that this is not the only path to get to exascale. We expect in the future that architectural diversity will increase. There's going to be more vendors, more accelerator technologies. We talked about the workflows. Some of the things I didn't talk much about, the mixed precision arithmetic that these machines can take advantage of. Higher order methods is another way to pack work onto a GPU. Data flow architectures. If you're in the CS community, you're going to see a lot of research coming on up soon on this kind of new architecture. Size, power, and weight, the swap constraints are going to dominate. This goes down into the microelectronics and materials layers. Again, it's these power considerations are going to be extremely important. And then finally, post-exascale, what are we looking at? Well, you're going to see an emergence of non-traditional architectures, in particular, quantum and neuromorphic. There's a lot of investment already going on in quantum and up and coming in neuromorphic. It's not clear how our algorithms are going to perform on these machines. That's part of the research being done, but you can in 10 years and beyond, you're going to start seeing these machines be out there. And then finally, I will close. This is the website to the DOE Exascale Computing Project. There's a lot of information there about applications and software technologies, and I invite you to go poke around and see what you can learn there. So I will close now and take your questions. Thank you.
Great, fantastic talk, Jim. It's a really tremendous overview and perspective of where we came from and where we're going. There are a couple of questions, and I'll just dive into those straight away. First one is from Kumar Vemaganti. It says, great talk, Jim. Could you comment about the exascale workflow in the presence of UQ, of uncertainty? How would UQ simulations fit into this framework?
Well, Yeah, that's a good one. Now, you know, historically, UQ was billed as a driver for exascale because in the context, we talk about embedded algorithms, right? There's embedded UQ, there's embedded sensitivity analysis and optimization that kind of goes along with it. So yes, UQ can very much be a huge driver for exascale. I think the challenge is going to be getting the UQ algorithms to be embedded in these codes. I mean, a lot of these applications are multi-physics. They have different modules, and to do UQ effectively, you have to build in the derivatives, the things that allow you to do things like polynomial chaos expansion and the like. So I think it's going to happen. It's going to be part of it. We're going to have to do UQ one way or the other, either through I think it's just going to be a toolbox of approaches. So that's a great question, but I will say it is very much a work in progress.
Thanks, Jim. Just one more. So you talk about quantum computing, and of course that's coming. Before that, the problem of linear solvers needs to be solved on for quantum computing, and that will really enable many of our workflows. But even before that, is there thought about, you talk about other accelerators for AI, TPUs? I mean, of course, that's very TensorFlow specific, but is there thinking along those lines, and would tensor processing units fit in? Yeah.
Yeah, I'm not the expert in those, but I do believe Summit already has some NVIDIA TPUs in there. And those are one of the accelerator paths to get there. So yeah, we have that'll be part of the equation. You know, you've got ASICs and you've got FPGAs and things like that as well that are on the horizon for other kinds of accelerators.
Okay, that brings us right up to the mark, and if there are no more questions coming through, I think we are close to done then. Thanks very much again. Like I said, a very nice perspective on things that are being done at the labs to enable these our progress in this direction, and doubtless we'll have much more to come from all the exciting stuff you pointed out. So thanks again.
Well, thank you. I appreciate it. And please reach out to me if you have any more questions.
Absolutely. Oh, I should just mention everybody that the 17th USNCCM is going to feature Jim and Sandia Labs in a leading role organizing that conference. So stay tuned
And I'm making a pitch for beautiful Albuquerque behind me.
So you can see it right behind you.
I hope to see you in 2023.
Okay. All right. Good. Great. Thanks, Jim.